Hello there, everybody. This is the two mathematicians, both of us
Hello.
this time.
Yep.
And today we're going to be looking at the Riemann hypothesis. Last week we looked at Fermat's last theorem, which is another famous maths problem. So we're just continuing with problems.
Yeah.
Yeah, straightforward. Okay. So the Riemann hypothesis, it all started with this person called Bernhard Riemann, and he was a German mathematician.
Tell me more.
Yeah, my pronunciation is very bad. If I'm spelling this wrong, just let me know. So Bernhard Riemann was born in 1826 and he died in 1866. And he was famous because he did a lot of work on numerical theory and lots of things like that. And a lot of his work was actually used. He discovered a maths that helped build an understanding of gravity, space, and time, which actually Einstein used later on for his theory of relativity. So actually,
I didn't know that. That's crazy.
yeah, Riemann, he did a lot of stuff for the maths world. And obviously, he's most famous for his Riemann hypothesis, which was proposed in 1859. So now we're in 2020, so still to this day, nobody has solved it. So overall, it's been 161 years since it's been shown to the world. But if you're watching this video at a time when the Riemann hypothesis has been solved, that's kind of cool.
Yeah, comment down below.
Comment down below the answer. But but obviously I don't think it's going to be solved for another 100 years or so. Maybe I'll be wrong. Maybe it gets solved tomorrow. Yeah.
Maybe we'll solve it right now. I don't know.
Yeah, maybe as we go through the video, we'll give you an answer. So yeah, so last week we looked at Fermat's last theorem. That took 360 years, I think, to solve. This one 160 years, so I'd say there's another 200 years till that 360 years is fulfilled.
This one's a little bit more complicated than Fermat's last theorem.
Yeah, this one's more relatively obscure, and it's so hard that there's actually a prize that's been given out. For anyone who can solve this, there is a prize of, I believe, $1 million, or is it 2 million?
It's $1 million. Yeah.
$1 million US. Oh, I said pounds.
It's one of the Millennium problems. So there's like a set of maths problems, and the Riemann hypothesis is on there. And if you prove it or disprove it, then you get $1 million prize.
So yeah, so we're going to prove it now, and then we'll get our $1 million. We'll share it between us.
Yeah, that's right. Let's prove it now.
60-40. I'll take 600,000. You take 400. Okay, so I'll pass over to you now, and you can explain the maths behind this great problem.
Sure. So I'm going to go on a new page, I think.
Okay. Yeah.
So it's all like based on this thing called the Riemann zeta function, which is I don't like that zeta. This is the Greek letter zeta, right? So that's the Greek letter zeta. And so this is the Riemann zeta function, which is basically like it's just defined by this. And it commonly uses S. I couldn't tell you why, but
okay, that's not a 5.
It looks like this, and it's a sum to infinity. So you can look at it like that from r equals 1 to infinity of 1 over r to the s, right? So whatever you put in it, s, will give you a value. And the idea is, for some values it converges, but for some values it diverges, right? So let's put in s as 2. So you get the Riemann zeta function of 2, which you can see is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, right? You get the picture. Yeah. Which Euler proved, Euler coming back, is a divergent sum, which means that it all tends to this limit, which is a really strange limit, but in this case it's pi squared over 6.
Oh, okay.
It's pretty crazy. Yeah. But this is true. If you put in 2 into the Riemann zeta function, you get pi squared over 6. So the idea is that for some values it diverges, but also for some values, it converges. For 2 it converges, but for some values it diverges, right? So if you put in -1, right, then you get, now I'm hesitant to write this, but you get 1 over 1 to the -1 plus 1 over 2 to the -1, right? Yeah. But that's just the same as 1 plus 2 plus 3,
Oh yeah.
right? Because you just flip the fraction.
1 over 1 plus 1 over half. 1 over half is the same as 2.
Exactly, which you think is just infinite, right? But actually, that's like, I don't want to cross this out, but that's kind of not the case, which is kind of counterintuitive. Yes, the answer is yes. If you add up all the numbers from 1 to infinity, it's not going to converge to a value. But the idea is actually, if you put in -1 into the Riemann zeta function, you get this value negative 1 over 12, which is kind of crazy. Why would you get negative 1 over 12? But that's because the Riemann zeta function isn't, I've kind of lied to you a bit. It's not exactly this. It's kind of defined in different ways based on where you are. So let me explain that. Let me draw a little graph. So we've got I'm going to do it like this. I'm going to do it like this, right? This is the real axis, and this is the complex plane, right? So complex real. So if you watch our videos on complex numbers, you can figure out what's going on here. But the idea is you've got 1, 2 there, 3 there, right? 4 there, and you've got -1 here, and -2 here, and -3, so on, right? And then you've got I, 2I. Correct me if I'm doing something wrong, because I haven't actually done. So on, right?
Because it's complex, we don't have to actually put down the I. We can just assume it's in terms of I. So we just put 1, 2, 3. But yeah, it's the right.
Oh, right. Okay, that's true. Okay, good point. But the idea is, like, we showed that the Riemann zeta function, which remember is this, infinity of 1 over r to the s. The point is, it's well defined for all values. Like if you put in s as 2, you can see that it converges to pi squared over 6. If you put in s as 3, you'll get some value, I don't know what it is, but it converges, which means it like tends towards this limit. So the idea is that for all values here, the Riemann zeta function is well defined, right? For these values, the function is well defined. But if you put in -1 and -2, we showed on the previous page that it looks like it diverges. It just goes to infinity. But so like it doesn't really make any sense. But the way mathematicians figure out what to do on the right side, on the left side in the negative real plane, is by using what's called analytic continuation, which I'm not going to get into the details of, but it involves things like derivatives. And it's basically you find this pattern of what the Riemann zeta function does on the right-hand side in this section here. If you like graph it, right? And then you kind of almost like continue the graph to make it look nice. But you can do that because there's only one possible continuation. So it makes sense for it to be that one. So the idea is that for all values here, the Riemann zeta function ends up being defined as well. Now, when I say it's defined here, it's not necessarily defined by this, right? So the idea is that the Riemann zeta function might actually encapsulate multiple things depending on where you are. So like for s is greater than 1, it might be that. But for s is negative, it could be something else, right? So that's the idea. It's not necessarily always defined by this. But now I hear you ask, what about this middle section? Well, that's where the Riemann hypothesis comes in. And it basically says, the Riemann hypothesis concerns all the zeros of this function. I'm going to erase a little bit of this because I'll clear it up. But the Riemann zeta function has certain zeros. And what I mean by that is just, where this is equal to 0, right? That's a 0. And some values are when s is -2, when s is -4, s is -6. Really, when s is just -2n, where n is, of course, a natural number. So all like the -2, -4, -6, -8, they're all zeros of the Riemann zeta function. The Riemann hypothesis says that all other zeros of this function lie on this line here. They all lie on this line. which means they lie on this line where that's 1 over 2. So that's a half, right? And that's the Riemann hypothesis, that all the other zeros of this Riemann zeta function lie on this line of s is a half. And it's been tested for like a trillion numbers, trillions of numbers, and it's tested true, but it's still not accepted as true because for mathematicians it needs to be tested for everything to be true. There you go.
That was cool. Yeah.
And it turns out it has connections to like prime numbers and the pattern of prime numbers. And I mean, frankly, I don't know what the pattern is, but there you go.
Yeah, because there's still the mystery of what's the pattern between prime numbers, how do you get from one to another? Because it starts off with 2, then you go to 3, but then you end up jumping big numbers once you get into the hundreds of thousands. So nobody knows.
It seems like there's no pattern, but the Riemann hypothesis, it can kind of be used to derive this way of finding how many prime numbers are between 1 and n. So like it can tell you how many prime numbers are between 1 and a trillion, 1 and 100. So in that way you can kind of find the distribution.
Yeah.
But it hasn't been proven. So this is the idea, is that if you can prove or disprove the Riemann hypothesis, that all the zeros, all the remaining zeros of this function lie on this line of s as a half, then you get the $1 million.
Well, let's hope it gets proven someday. Or maybe because inflation, by the time it does get proven, that $1 million is
That's true. I hadn't considered inflation. I don't know if it adjusts for inflation.
I don't know, because I heard about it about 10 years ago and it was still $1 million. So
yeah, well, you might end up getting a lot more than $1 million.
So yeah, there you have it. Thank you for watching this video, and remember, maths is the way.
Maths is the way.